Today on Computer Science for Humans, we are going to be talking about Big O notation, a shorthand notation for algorithm efficiency that has terrorized college students and new employees for a long time. My name is Reagan, this is Computer Science for Humans, and today, we're just going to talk a little bit about Big O and help you understand it a little bit better. And don't worry, we will have examples, they'll be at the end. Feel free to skip through this video to whichever part is the most useful to you. I'll have the chapters down below. So without further ado, let's begin. Big O confuses a lot of people. And that's because most people who teach it as if it is math. And to be fair, they're right, but that doesn't mean that's the only way to look at it. And I find it's a lot easier to understand if you kind of ignore the mathy part and leave that to the mathematicians. So we're going to be talking about Big O in layman's terms. If you want the really advanced mathy version of Big O notation, let me know in the comments below. Leave a like on the video, and if enough people ask for it, I'll make a video on that too. But for this, we're just going to talk about the basic Big O notation, the kind that everybody learns in college and most people end up having to use at some point in an interview. Jargon is one of my biggest pet peeves, and it makes the learning process a lot harder for new people. So I'm gonna go ahead and explain some of the jargon up front. I try not to use it generally, but here are some terms that if you are new to computer science, you may not already know. So it's good to have a definition in mind in case I slip up and use jargon, which probably will happen. I've been doing this a while. The first piece of jargon you need to know is function. If you've been coding for any length of time, you already probably know what this is, but it's important to note because there is math involved, we're also talking about mathematical functions sometimes. And basically all a function is some code or some math that takes some inputs and gives you an output. I like to describe it as a coffee machine. You put in the coffee beans and water and it gives you coffee. That coffee machine is a function that takes parameters of beans and water and has an output of coffee. The next piece of jargon to know is in, and that's the letter N. You're going to be hearing this one a lot because there's not really a way to talk about Big O without mentioning N. The important thing here is N is how many things are in the data set that we're working with. The next one is element, and this one's just a little more niche. Some people don't know it, especially if you're new. An element is a thing inside of a list. So if I have a list of 5 people, each person is an element in my list of people. Finally, we've got iteration. Iteration is something that if you've been in the corporate world, you've definitely heard at some point, and if you've been programming for long, you've definitely heard. But in case you're new, an iteration is one time that you do a thing. So if I'm going to do things 5 times, there are going to be 5 iterations. And it's also important to note that usually, not always, but usually an iteration also implies that you're making some kind of progress. So for example, if I want to walk across the room and that takes 5 steps, each step is an iteration and I've made progress each time I've taken that step. Related to this, if you're iterating over something, that basically just means you're going through each part of it and usually doing something to the parts when you get there. There is one more piece of jargon I just thought of, and that is data structure. If you don't know what a data structure is and you somehow found this video, I'm actually impressed, but just in case. A data structure is just some code that is meant to organize a large amount of data. The most common examples and the ones I try to stick to for the most part in videos like this are lists. A list is a data structure because it takes random data and puts it into some kind of structured format, aka a list. And for most of this video, we're just going to assume we have a list because the same principles apply regardless of whether you're using a list or not. And pretty much everybody understands how lists work. Now that we've got all that stuff out of the way, let's talk about the basics of Big O notation. It's worth mentioning here that there are 2 sort of different kinds of Big O notation. I call them the regular kind and the complicated kind. We're just talking about the regular kind of Big O right now. We're not worrying about like the really nitty-gritty detailed calculations and really mathy stuff. That'll be for a totally different video. Again, if you want a video like that, let me know and I'd be happy to make it as long as enough people actually want to watch it. So when talking about regular Big O, I'll be calling it just Big O from the rest of this video. There are a few assumptions that we are going to make. First, we're going to assume that there is a piece of code. We're going to call that piece of code F, or F of N. F is short for function. And this is, like I said, it's a little mathy. This is where the math terminology starts to come in. The second thing that we are going to assume is that our function F acts on a list. Now, it can be another data structure like a tree or a heap, which I guess is basically just a fancy tree. But anyway, it can act on just about anything, any kind of data structure. But we're just going to assume that our F is acting on a list because lists are easy to understand. The size of that list is N. Just like we mentioned before in the jargon, N is just how many elements or how many things are in that list. And when we talk about Big O, we are going to assume that N is gigantic, that this list has way too many things in it. The last assumption we're going to make is that anything that does not directly affect n doesn't matter. And some of this will make a little more sense as we go on too, but just keep those in the back of your mind. The purpose of big O is to tell us how efficient F is going to be when N gets really, really big. There are several different categories of big O. These are the most commonly occurring ones, and you'll see them all over the place. And each one is kind of a simplified version of an entire genre of functions that have similar big O notations. So we'll start with what I consider the default big O, and that's big O of N. This is kind of the baseline that we compare all other big O's to. And again, throughout all of this, remember, big O is bad, little big O is good, because big O means your program is slow, little big O means your program is fast. There's a huge asterisk here that this only applies if you've got like a billion things in your data set, or more than a billion. If you've got like 5 things, then none of big O even matters. But that's a whole other conversation for another day. I know I've heard the Primogen talk about it once or twice as well. So big O of N, what does this mean? This means that the code happens once for everything in your list. It's kind of like saying for each. The easiest way to recognize big O of N is if you look and you see a for loop. And the for loop is just a basic, simple for loop. We call this linear. Basically means there's a 1-to-1 ratio of I do one thing and I make one progress through the list. The next most common one you're going to see is big O of n squared. Big O of n squared basically means for each thing in the list, you are doing something. It's a loop within a loop. Big O of n squared is generally considered horrible in terms of how slow or fast something is. N is really not that good because if you think about it, big O of n means if I have a billion things in the list, it's going to run a billion times. Big O of n squared means if I have a billion things in the list, it's going to run a billion times. A billion times. So you can see how quickly that gets out of control. And when you consider the fact that a company like Google or Facebook is going to be dealing with literal petabytes of data, if you have big O of n squared, you are dealing with numbers that are beyond human comprehension. I don't even know the name. Just look at this thing. So big O of n squared is bad. And usually, not always, but usually it means you have a loop inside of a loop. So still going up the chain of worse and worse and worse big O's, we have big O of n to the something else. So pretty much anything bigger than 2 is going to be bad. The bigger it is than 2, the worse it is. Going up this chain, you can actually get to quite a few little interesting things that are worse than O to the power of something. And then there are things like n factorial that is even slower than n squared, or I think even n cubed. It's ridiculously slow. What's the other one? Oh yeah, x to the n. So that's where basically n is the power instead of being raised to the power. And honestly, if your code is that inefficient, then you're either in a really situation or it's time to rethink the way you've written your code. But those are pretty niche and you don't really end up seeing those very often. If you have ever seen something like n factorial or x to the n as the big O of something you've used in real life, please let me know. I would love to hear the story behind that. The main general rule to take away from this part is the more for loops you have inside of each other, the worse it is. And usually the number of for loops you have that are all nested inside of each other is going to be the power that n is raised to. And then if it's x to the n, well, that would mean you have n for loops. Anyway, so that's all the stuff that's bigger than n. Now let's go smaller than n. How do we get more efficient than a 1-to-1 ratio? So right below n, we have log of n. If you're not very mathy, then this is going to be weird. Logarithms are kind of obnoxious, but basically you can think them as a reverse to the power of. Logarithms are really weird mathematically. They're a whole rabbit hole. I'm sure somebody other than me has done a much better video on how logarithms work. I'll have a link down below for you to click and probably in the card to a math YouTuber. They're going to do a better job explaining logarithms than I can. But I just think about it in terms of it's a reverse power. So how do we recognize these in our code? Log of n usually looks like taking the data set and halving it on each iteration. And we'll go over some examples later so you can see those a little better. Below log of n, we have big O of 1. This is as fast as it gets, at least in terms of gigantic data sets. This one's a little weird to a lot of people because it's kind of abstract. So 1 is not literally the number 1. What 1 is saying, the time it takes to do your algorithm is not in any way related to how many things you have in your list. So big O of 1 means if I have 3 things in my list, it's the same speed as if I have 100 things in my list, and it's the same speed as if I have 1 trillion things in my list. Big O of 1 means I don't care, it's all the same. The way I like to think about big O of 1 is if you imagine you have a friend and you're going to their house and they live in a city, you're not very familiar with the city. Do you go to every house in the city and ask that person, are you my friend? Oh no, sorry, I'll go next door. No, of course you don't do that. You don't even do that in the subdivision unless you get lost. If you're like me, you pull up Google Maps or whatever map you prefer to use, and you go directly to their house. It doesn't matter how many houses there are in that city, you're always going straight to your friend. And that's a big O of 1. The most obvious example of big O of 1 in code is usually something like an array or a hash map or a dictionary, where you have a list of items and each one has a label. And if you have that label, you can go directly to the item you want and get it. So there's one more that comes up a lot that I want to talk about. And this one I've saved to last because it's weird. And that is in log of n, or in times log of n. And this one is conceptually really hard to kind of wrap your mind around. So for me, I just break it up into two pieces. Specifically, you've got log of n, so you're cutting the data set in half each time, but you have to do that for each element of the list. Most sorting algorithms are this way. Okay, so I've got some examples here for you, and we're gonna go through these one by one, and I'll explain the process of figuring out the big O for each one. You don't have to memorize these. This is mostly to give you the ability to start recognizing patterns. And if you are in a class, you'll probably see a lot more of these and other examples in that class. I've tried to include some of the more devious examples that professors like to give to throw you off and trick you into thinking it's one big O when it's another, but I can't account for all of them. But this should be enough to get you started and get you thinking outside of the box, enough to pass a quiz or an interview. Okay, so let's take a look at this first one here. If you want, go ahead and pause the video for a few seconds to see if you can figure out what this does. Fair warning, not all of these functions do things that actually make sense to do. It's more about calculating the big O overall rather than actually doing something useful. So whenever I'm calculating big O, the very first thing I look at is the loops. You can already see this is a for loop, and it's just one for loop. So most likely it's probably going to be big O of 1. I mean n. Most likely it's going to be big O of n because of the single for loop. But the main thing to look for is, does it hit every single element of the array once? In this case, we start at 0, kind of typical, and then we go to, stop popping up please, and then we go all the way up to array.length, also pretty typical, and I++, which is typical. So we are going from the start to the end one by one. That means we're going over each thing. And because we're going over each thing, that is big O of n. Now inside of this, we've got this if statement. If statements generally are just going to be big O of 1 because it's just a thing that you do. There's no relation at all to the number of elements in this array. And this is no exception. It is important to notice that this is a big O of 1 lookup. So it takes one action to go into the array, go to number I, and pick it up. That's what this is doing. And then it checks to see if it's equal to the target. This is big O of 1 because it's an array. If we had something like, say array was a linked list, and we did something like arr.get I, this is totally different now, because a linked list, unless you've got some fancy indexing going on, a linked list has to loop through the linked list to get to that spot. It has to start at the beginning and loop through each element until it gets to I. So that would be one way they could throw in a secret loop that you may not notice immediately. So if it was a linked list, then this would be big O of n as well, because it has to loop through. But right now we're just dealing with big O of 1 because it's an array lookup. Another tricky thing that they could do to make this one more confusing is, instead of arr.length, you could do arr.length divided by 2. But what do you think the big O for this is? If you said big O of n divided by 2, you would be correct. If you said big O of n, you are also correct. Because this is array of length divided by 2, we're only going halfway through the list. So that means instead of n, it's half of n, which is n divided by 2. However, because big O is an abstraction, it's not meant to be truly fully literal. We usually just simplify big O of n over 2 to just be big O of n. This is why I called big O of n a category, is because big O of n includes anything that's not exponential in growth or logarithmic in growth. It's anything that's more or less linear, more or less 1-to-1. So just keep an eye out for that. It's worth noting as well that if I did times 2 here instead of divided by 2, it would still be big O of n or big O of 2n. Those are also both in the big O of n category. For our next example, we have this function. Again, feel free to pause it if you want to take a second and figure out what exactly this does. What do you think the big O for this is? If you said big O of n squared, you would be correct, because we've got a for loop, and this for loop goes over the entire array from start to finish, one by one. And then we've got a second for loop, which goes over the whole array from finish to start, one by one. That's the tricky part of this. So that means we have big O of n for the first loop, big O of n for the second loop. And because they are inside of each other, do we multiply or add them? We multiply. So that's n times n, which ends up being n squared. And again, we have the thing right here where if this was a linked list, that would be n cubed because this would actually this would be another loop over n. So technically it would be big O of n, big O of n, big O of n divided by 2, which is n times n over 2, or n times n if we're simplifying it. So now number 3, now we're getting past the really basic examples. Those were some really basic ones. This is when it starts to get a little more interesting. Again, feel free to pause it if you want to. If you're thinking that this is big O of n, you are correct. This one's a tricky one. So first off, we can ignore this. See if I can select it because it doesn't really matter. Same with this. For big O, we don't care about all that. We just care about the loops, the things that happen multiple times. We can see that it starts at 0. It goes to the length plus 1,000 and then I plus plus. So that plus 1,000, this is n. Dot length is going to be n when it refers to the array of things we're looking at. So this first loop is big O of n plus 1,000. And once again, keep an eye out for these. If it's a linked list or something like that, this would be another n, but for now it's not. So we've got big O of n plus 1,000. And then down below, we have this. If you're not familiar with this notation for a for loop, you can treat this as if it says for each and treat this as if it said in. So it's for each int called thing in the array, basically meaning loop through the array and put each element into this variable and then do all this. So this is just a for loop and it goes from start to finish in the array. So this is big O of n. And because they are not inside of each other, we're going to add them together. So we have big O of n plus 1,000 plus big O of n. Using math rules, we can simplify this to big O of n plus 1,000 plus n, or O of 2n plus 1,000. As we get bigger and bigger with n, multiplying it by 2 doesn't really matter, and adding 1,000 doesn't really matter. So we end up with big O of n. And I know that's weird. It's just the way the math works out. Here are some graphs of what this looks like, what these different simplifications look like. You can see that it's basically the same graph, just in different places. That's why we just kind of say, okay, that progresses like big O of n. They're both a line. They're both linear. So we're like, it's in that genre of being lines. More interesting stuff happening here. I'll give you a second to pause if you want to. So this one's big enough. Let's just go through them one by one. So first, we've got big O of n, because it's going start to finish one by one. Then inside of that, we've got big O of n, because it's going finish to start one by one. Then we've got our lookup here that's just a big O of 1. This is just a big O of 1 because it's just math. And then we come down here. And this is big O of 1. Or sorry, I keep saying 1. N. Big O of n. And then we do some math, so we don't care about all that. And then we get down to the bottom. So what do we have? We have big O of n times big O of n, because they're inside of each other. And then plus, because this third one is not inside of the other ones, big O of n. So that becomes big O of n squared plus big O of n. And if we look at the charts for big O of n squared versus big O of n squared is so much bigger than big O of n that we are just going to throw away the big O of n. It's just so small in comparison that it's irrelevant. So this simplifies big O of n squared. So notice that what we did here, looking at the shapes again, these are different shapes. We've got n squared shape, which is that, and then we've got n shape, which is just a line. When we have two different shapes, if they are added together but not multiplied, because multiplying makes a new shape, if they are added together, then we're just gonna get rid of the smallest shape, because compared to the big shape, it is completely inconsequential. And again, that's because this simplified big O is all about putting your code into a genre of big O notations, rather than getting the precise big O notation, because frankly, precise big O notation is completely useless. And if you have evidence to the contrary of that, let me know, please. I would love to know where in the world or why or how the precision version of big O is actually useful. Moving on. This one is not hard, but it is a lot. Feel free to take a second to think about it if you want. Just realized I had left this print statement in here from earlier. Reagan, you can probably just edit this out, maybe. So it may have been given away by it saying quintic operation. This is big O of n, big O of n, big O of n, big O of n, big O of n. So we have big O of n. Oops, let's comment this. Big O of n to the 5th. If you ever end up in this situation, one of two things is the case. Option 1, you have done something horribly, you have made a very big mess for yourself. Or 2, the problem you're solving is really, really convoluted and hard to solve. Or both. There are problems out there that require something like this. But yeah, so this is big O of n to the 5th. And generally speaking, as long as the for loops are actually looping through the whole array or whatever list it has, you really can just count the loops. and we've got 5 loops, so it's big O of n to the 5th. But you do have to watch out for, a lot of professors will do sneaky things like this, where all of a sudden this loop is no longer actually looping over n. Now it's just going to 500. And in this case, we just consider that constant time because 500 is a constant. It doesn't change with the array's length. So keep an eye out for that. If that was the case, then that would become n times 500 times n. So it would be the second one. I'll put it up here. O of n to the 4th times 500, or O of 500 n to the 4th, or simplified 2 n to the 4th. Keep an eye out for sneaky things like that. Let's go on to our second to last example. Take a minute to look at this one, see if you can figure it out. This is where we're getting a little weirder. If you said big O of log of n, you would be correct. Remember, log of n is kind of the reverse exponential. It's the one that's shaped like this. So the question here is, how could I tell, or how could you tell, that it was log of n and not something else? The key is this I equals I times 2. So remember, with logs, with logarithms, the key feature is that you're halving the number of things you have to deal with each time you iterate. And this section of the for loop happens each time you iterate. It's how you go from one step to the next. In this case, every time we go to the next step, we don't add 1 to I, we double it. So I is going to go, well, actually, I just realized I made an infinite loop. If you caught that, if you got big O of infinity, then kudos to you, because that would be spot on. The reason is because I equals I plus 2, I is currently 0, so, or I times 2, and that's currently 0. So we have 0, or I equals 0 times 2, which is 0, which is never going to be greater than array.length, because it's always going to be 0. So I have accidentally created an infinite loop. Let's change this to 1. Note that the difference between O of n and O of n minus 1 is completely trivial, and we do not care at all. Now that it's not big O of infinity, it's big O of log of n, because each jump is twice as big as the last. So we're going to go through the loop at essentially an exponential pace. And when you progress at an exponential pace, the amount of time it takes to get to the end progresses at a logarithmic pace. You can think of it as the more faster you go with each step, the less steps you have to take to finish the race. Again, logs are weird. There's not a simple, easy way to think about a logarithm other than chopping it in half each time. Last example that I have not numbered properly. So here we have this one and this one. This is a weird one. Go ahead and take a second if you want. So let's take this one step at a time, because this is definitely weirder than most of the others. So first off, we start at the beginning. We go one by one. That's good. But we're not just going to the end. We're going to the end times the end times the end, which is another way of saying n cubed. This is an n cubed loop. Then we've got this. We've got n cubed again, but this time we're not going one by one. We are doubling each time. So it's O of n cubed, and we're progressing at that's the size. And then we are progressing at a rate of big O of n squared. Squared is because we're doubling each time, which means, remember, when we go forward at n squared exponentially, the big O increases like a log. So our second big O is log of n, or more specifically, it's going to be log of the amount of stuff we're going over, which in this case is n cubed. Yeah, okay. I had to double check myself a couple times on this one because it is very weird, but we end up with big O of log of n because of this. But instead of progressing over n, we're progressing over n cubed, because n cubed is the length of the array that we're going over. It's log n cubed. So what we end up with at the end of this whole function is big O of n cubed plus big O of log of n cubed. The logarithm of something is always going to be smaller than it itself. Because of that, we throw away the big O of log n cubed, and we end up with just big O of n cubed. Hopefully, you don't have to deal with very many that are like this. But I have seen stuff like this thrown out by interviewers and professors. So it can get weird like this. And stuff like this is usually why people don't like big O. Oh, whoops. I just realized I was so tricky, I tricked myself. This one is not big O of n. The loop loops over big O of n. That's true, but I did not account for this if statement. I had forgotten about this. So if you were paying attention, you may have noticed this. We are saying if k is greater than or equal to b, then reset k and start over. Hopefully you ended up at big O of n squared. So this is basically a sneaky way of doing a for loop in a for loop. Since every time k catches up to where b is, b increases by 1, and then k resets to 0, you're effectively going whoop, 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 which is essentially what is being done by an n squared loop. So you're effectively going over each element of the array once per element of the array. But yeah, this one's super weird. And that's Big O in a nutshell. You now know more than most people about Big O, and you know about as much as most professionals. If you have any questions or clarifications, or if you disagree with anything I said or think I calculated a Big O wrong, let me know in the comments. I'm always up for hearing that kind of stuff. Also, let me know if you want me to do a more advanced Big O video where we cover things like Big Omega and Big whatever the other one is. I can't remember, Omicron or something. It's another letter from another language. Let me know if you want me to cover that too. I'm happy to make that video if there's people that actually want it. Hopefully this made sense. If you got value out of it, don't forget to press the little buttons down below. Thanks for sticking through it with me this long through Big O. I know that Big O's hard. My name is Reagan. This has been Computer Science for Humans, and I look forward to seeing you in the next video.